It was a really nice pen. I'm like, I'm not throwing this away. It's actually really nice.
That's why you want it back.
I'm getting it back.
Is that it?
You got it.
I was like, hey, this is kind of nice. I'm gonna check papers with that at some point.
Sorry.
All right. Okay. All right. So first and foremost here, notes out, please. Calculators out. If you need to go borrow a calculator, you know where the drill is. If somebody gets back there, just check that I have all 10 before we start today.
Oh, I'll check if you got all 10. This one, oh, you got all 10.
All right, good. It's like, just making sure. Check your
Oh. I don't know.
Never forget.
Yeah, I have one of my charts.
First day, you probably pick up like 20. Okay.
The second day of school, I was like looking around for a hole.
Oh my god, how many
Someone's everywhere. And I just saw that. Just like, I don't think he has a
Okay.
What did you do?
All right. Hey, today, here's what I want to cover. I want to cover the exponents again one more time. We got to get to those more difficult formulas, the actual laws of exponents, and then the goal is to talk about like why did they create it in the first place? Because obviously we use it in algebra and algebra 2 and pre-calculus. What was the original purpose to having like an exponent? That was like, because that's one of those things that people just naturally forget. Other than just being shorthand for multiplying a number a lot of times, why was it originally created? And that's what we're going to look at today.
Did you do something like really important yesterday?
We just talked about laws of exponents. We did a slight review and then I gave some time to work.
Oh, we got homework?
Yeah, we had homework. Well, we didn't get homework. We had homework that was due. Yeah.
Oh.
So, okay. All right. We'll get to that later. Okay. Now, here's the idea. Let's talk about those basic three laws. I'll put one example of each, like right here, and then we're gonna get to the new law today, like the new three that are kind of more challenging. So, laws of exponents. This is the second section of this prerequisite. So it's like P.2 if you want to keep track of sections. Some people like to know what the section they're in if they're using that online textbook. So laws of exponents. Okay, so here's the idea. On this particular section, the three basic laws. Number one was the product rule. Okay, because some of you like the names of those. The product rule is when you just multiply two things that have exponents in them. So one of the examples I did yesterday was something very similar to this, where you take one item and you're multiplying it by another. Just like that. You can multiply anything in the world. They don't even have to match. You can just multiply. When you add, they have to match, or subtract, they have to match, but multiplying, you can multiply anything in the world. Now, what we talked about yesterday was how to do this again. I walked through the real math, and then I walked through the shortcut. The shortcut is just the only numbers we can multiply are the 3 and the 5. That makes 15. Everything else is just a variable. We don't know it. That's what a variable stands for. It's an unknown. We just throw those in the back. So you just tack all the letters in the back, and since you can't do anything with them, they would just like combine up. So the shortcut is you add the variables together. So there's 3 x's, because you have 2 here and 1 there. You have 5 y's, because you have 1 and 4, and then there's 3 z's left over. Like that's the shortcut, but the real math behind it is you're just throwing all the letters in the back. You can't do anything with them, so they just kind of just all combine up again, because you just rearrange them. That is what we talked about yesterday. Is there any questions about the shortcut though? I'm betting on 99% of you will probably just use the shortcut. You probably still remember it. You just need to do a refresher on it. You just combine those letters. Second rule we had, the second law, which was the power rule. The power rule is where you have items inside a parenthesis and you're putting a power on the parenthesis itself. So, for instance, I think we did something very similar to this yesterday. Something like this, where you have multiple items in a parenthesis, but you have a power on it. We talked about the real math that's involved here, but the shortcut was you're basically just distributing that power through the actual parenthesis. So the 4 gets the power, the x gets the power, and the y gets the power. And so this ends up being 64, x to the 3rd, y to the 3rd. questions at all about that? Okay, that was one of the last, rules we talked about. The third rule is basically just a continuation of that one. So the third rule was a power of a power. Power of a power rule. So you're putting powers with powers on the parenthesis already. So, example way I think we did yesterday was like y to the fifth, and we're going to put it to the power of 3. That type of thing. Well, the trick is, it's kind of like rule 2. The power goes inside, but when it goes inside, since there's already powers there, you multiply them together. So this ends up being a y to the 15th. You multiply. Now again, the real math behind it is that you actually have 3 of these parentheses, so y to the 5th, y to the 5th, y to the 5th, and that's why it makes 15 of them. That's what exponents mean. We have 3 of those bases. Questions with the 3 basic rules from yesterday. That's all we did. I think I did one example of each. Then I gave you some time to work on that page 15 stuff. That was the stuff with basic expressions, variables, plugging stuff in. Okay, questions with those. Okay, now obviously, one of the things we have not discussed yet, they're going to start mixing these all together. It's like it should be like, when you saw these yesterday, the first thing you should think of is like, I'm going to get a problem that has all 3 of those in one problem. So, for instance, 2x to the 3rd, y to the 4th, all to the 2nd power, 5x, y to the 5th, and we're going to put this to the 3rd power. Like, you should expect a problem like that, because they're testing whether you understand what the basic laws are, and number 2, can you combine them into one problem? Now, I'm not going to start you off that crazy. I would probably start you with problems where they don't have the powers on them first. Multiply those, maybe do a couple where you have to distribute the power in. Then, the next 4 problems you'd have some like this where they get difficult and difficult, right? So, to do this problem, what I would do first, I would deal with the powers first. So I would distribute this power of 2 into this parenthesis to everything. At the same time, I'll distribute this power of 3 into this parenthesis to everything. And whatever those answers are, the last step is I'll multiply last. Because if you think about the order of operations, you have to do anything inside the parentheses first. I can't really do anything inside. The next thing you look for is you do exponents. So I do the exponents next. Then the last thing I always do is I multiply everything together. So, distributing the power of 2, what's 2 to the 2nd power? 4. X to the 3rd to the 2nd power. X to the 6, because you have to multiply, that's that 3rd rule where you have to multiply the powers. Y to the 4th to the 2nd power is y to the 8th. Okay, so I distribute the powers. Second one, distribute the power of 3. 5 to the 3rd power. 125. X to the 3rd, y to the 15th. Alright, there you go. Alright, questions at all about the basic concepts? Okay, now, finishing this out. Multiplying these numbers out, like actually doing the math here, I can take 4 times 125. Let's see.
500.
Yeah.
Thank you. Alright, so 500, the x's, you have 9 of them, and then the y's, you're going to have, what, 23 of those? Okay, there's your final answer. Remember, order of operations. Parentheses first, exponents, then multiply and divide, and if you have any adding and subtracting, you do that last. Remember, you can only add and subtract if they have the same variables with the same powers on those variables. Okay, questions at all about the first 3 laws? Okay, I'm betting on you probably remember it. It's been a while though, so you needed a refresher. Okay, the next, I don't know if there's 3 laws, but I know there's quite a few. These are where these are rules that most people have never been taught the real math. You've learned shortcuts over the years, but you never see why. That's what I want to talk about today, is these next, I'm gonna call them 3 laws, because that's how I've learned them. I'm gonna call the next 3, and then we'll do examples, and I'll try to mix them together. Then the last step is I want to do scientific notation today. And we'll be done with a couple minutes to spare, and we're good to go. So here's the idea. Let's introduce these next 3. Now, here's my question. You want these left on the board just for a little bit?
No.
You guys can remember these? Okay.
I think the two are what they
All right. Okay, let's do these next 3 rules here. That's how I've learned them. So, first rule.
Is this just like the 4th rule? Or is it different?
4th rule, I guess, yeah. 4th rule.
Okay. I
So,
didn't know.
sorry, if you want to continue the number, it's 4. It's called the cancellation rule. It's how you divide. So I've called it the cancellation rule. I believe the book refers to it as the quotient rule. So I'll put quotient here. So I want to keep the wording the same in case you're confused when you look at the book. It's called the quotient rule. I call it cancellation. You're literally just canceling out letters. It's when you're putting variables top and bottom that match, right? They match, up and down. Now, I can have more than one set of letters. I'll do a more rigorous example here in a second, but the idea is that these would actually cancel out, and you're left with variables on where most of them are found. So like if there's more x on the top, that's what they'll be left at. And what you do is you just subtract these powers from each other. So it's x to the second, right? You get rid of one of each. So you're taking away 1 from each of these. That's basically what you're doing. Now, since there's nothing left on the bottom, you just put a 1 down there. 1 goes everywhere, because 1's in front of everything. It's a leading coefficient, so there's still 1 down there. Now, if you don't want to write the 1, I have no problem with it. Just write x squared, you're good. All right, questions with number 4, the 4th rule. Now, obviously, I want to do something a little more rigorous than that. I'll put one where there's multiple letters going on, and you can cancel. But this is like the number 4th rule that I remember learning when I was in school. It's called the cancellation property. So let me make this a little more challenging here. Not like crazy, but just a little more. So let's go with like 15x y to the 3rd z squared, 25x squared y z to the 17th. Okay. So, just taking this problem, you don't have to move anything, you're just canceling stuff out up and down. Now, how numbers work, like actual digits, you find their greatest common factor and you just divide them by it. Or just, if you know that they both have a 5 in common, divide them both by 5. They both have a 2 in common, divide them both by 2. Like you just go as far as you can until you can't do that any further. So like for 25 and 15, they both have 5s in common, I'll divide them both by 5. So 15 divided by 5 is 3, 25 divided by 5 is 5. And if I could go further, I would keep doing that. So basically what I always do is I just, just check the prime numbers, like 2, 3, 5, 7. Eventually you'll get them all. Now, for x's, where are they going to be left at? Bottom. There's more of them on the bottom. So, I'll leave the x on the bottom. I get rid of the 1 off the top, 1 off the bottom, you'll have 1 left down there. Okay, what about the y's? Where are most of them found? Top, I'm going to leave them up there. And I'm going to get rid of the 1 off the bottom, so there will be 2 left on the top. And the z's, there's clearly more on the bottom, so I'm going to leave the z on the bottom. And there's going to be, what, 15 of them left? Because I take away 2 from each.
Here's the volume.
All right, questions with the whole cancellation idea. Now, obviously, cancellation, this rule would come after you distribute powers through parentheses, because that's exponents. It would be multiplying and dividing, so you could cancel stuff before you want to multiply 2 fractions together, that type of thing. It's just one of those rules, like, it's division, right? You're just canceling stuff. That's actually, the concept of what I'm doing here is really similar with how I just dealt with the numbers out front. So, for instance, 15, you don't have to write this, but the 15 is 3 times 5. And I'll just call it like the x, and on the bottom, the 25 is 5 times 5. And the x's on the bottom is x and x. Right, there's 2 x's. Now, I'm not obviously writing everything there. This is just an example of it, right? Well, dealing with the numbers is the same way that I deal with letters. If they match top and bottom, they literally cancel out. if they match top and bottom, they literally cancel out. That's why there's a 3 and a 5 left, and there's an X on the bottom. It's the same concept. Most people never get to learn that real math. They just learn the shortcuts, but they never understand like why is it ending up being the answer that it is. It's because you would actually separate everything else in what they call expanded form, where you separate them all into like individual letters and numbers, and then just cross them out as you go. Questions with that concept? Okay. All right. That's rule 4. Rule 5. Okay. Rule 5. 0 exponent. So y to the 0 power. Y to the 0, or anything to the 0 power, could be a whole parenthesis, if you will, is always the number 1, no matter what it is. Anything to the 0 power is a 1. Now, I know in Algebra 2 they just say that. Boom, it's a 1, you move on. They just say things cancel out. That's not true. You probably have never been taught to read math before. So, here's the idea.
Sing them.
Who would have thought she's one that great teacher?
Who would have thought?
Okay, this is a part maybe off to the side. I actually want you to write this down. This will actually help us. I'm going to actually keep using this chart to help us with the next rule. So I'm going to leave this on the board for a little bit. Okay, 3 to the 3rd power. What does this actually mean? You have 3 3s, right? So you have 3 of those bases.
Genesis Winter, please come to the office. Genesis Winter.
Okay, so you got 3 of those bases. So 3 times 3 times 3, that's 27. All right, so you have 27 from 3 times 3 times 3. All right, so now, I'm going to write that down. Now, when you go down to the next row, 3 to the 2nd, that means you just have 2 of those bases, right? That's what the exponents mean. So that's a 9. 3 to the 1st, you have 1 of the bases, that's why the answer is 3. Now, what most people don't think of is the concept of like that pattern. When you go up a power, you multiply by another base. So if I go up a power, I just multiply by 1 more of the bases.
So you draw it 3 by 3.
So yeah, so exactly. So if you're going down the rung, you're just dividing by the base, right? You're dividing by whatever that base was. That gets you to the 9. You divide this by 3 again, it takes you to the 3. So if I went 3 to the 0, you go down 1 of the rungs again, and what do I divide by? 3. 3 again. What's 3 divided by 3? 1. That's the concept of why it works.
3.
Because when you're going down powers, you're dividing by whatever that base was, because you're going 1 less. Does that make sense? Why it's always a 1?
Yeah.
No matter what it is. It could be the biggest parenthesis in the world with hundreds of letters and powers and crazy things going on, and the whole parenthesis has a 0 on it. The answer is 1. You don't even have to do anything. It's just 1. It just, everything cancels out. I know for a fact that's one of the ACT questions. They give you this really complicated thing. One of the parentheses has a power 0 on it. That literally goes away. Turns out to be a 1, and you move on. All right. Moving on to one of the last rules here that we need to get. Rule 6. The negative exponent rule. Negative exponent. So let's say that I'm gonna make up an example here. Let's say that this is my problem. You have a negative exponent. Now, on this example, what item has a negative power? Just the x. You would move it to the other side of the fraction bar. So this would be the answer. The 3 would stay where it's at. The x will move to the bottom, and the y will stay down there. Because only items with negative powers actually move to the other side of the fraction bar. So if it was on the bottom, it would move to the top. Now, if you didn't have a fraction bar, introduce one, and then move that variable to the other side of it. Questions at all about what a negative exponent is? Now, here's the reason why. If you go and you follow my chart I just showed you a little bit ago, and I go 3 to the negative 1, we're following the same pattern. I dropped a power, you have to divide by the base again. So whatever your answer was, you're dividing by the base. That's why the 3 literally looks like it moved to the other side. So it looks like it dropped down to the bottom of the fraction because it's being divided by that base one more time. If I had 3 to the negative second, well, it would be that answer a little bit ago with another 3 on the bottom because you have to divide by the base again. That's why it's a 9 on the bottom, 1 over 3 to the second. Okay, questions at all about this concept? Okay. Once you see them, you're like, okay, that makes sense. How everything kind of connects together and how they're always working. But it all comes back to, do you even understand the definition of what an exponent is? Like that it's repeating that base so many times, or how it moves around. All right, last thing today. This is my absolute last thing. We've done all these examples. We've talked about every rule, talked about some tough problems, some easy ones. Why did they even create it in the first place? Like that's the concept. Like what, other than algebra when we have variables, where did an exponent originally come from? And you have to think back to like kind of the level of technology that they had at the time. You know, calculators have advanced since the 70s to a point where they're pocket. I mean, they're in your cell phones. Some of those original calculators were pretty thick. They didn't really do anything other than add and subtract. They couldn't even multiply yet. But they've eventually got to a point where they're large enough and they have enough memory that they can do some serious math. Like the concept is, like these newer calculators can do more calculations than some of those original cars could. That came out in like the 20s and 30s because the actual computer chips on the inside are more advanced. Well, the idea is that why they originally created this idea of like exponents is to do really large numbers. Because they didn't have variables. They didn't, you know, if you think your parents always say like, when we had math, we didn't have letters and numbers mixed together. Because they're right. They were just doing adding, subtracting, multiplying, dividing, and just learning how to do that for whatever concept they were working on. Well, if we're dealing with really big numbers, let's say something like this. Okay, let's say we're doing a problem like that, right? And we're trying to multiply these together. A calculator in like the 70s wouldn't even be able to handle that problem because it would be off the screen. It would be too many digits long. It wouldn't be able to compute it. It would say error because they didn't have enough memory to actually show up across the screen. These calculators anymore, they can go as many numbers as you want. You just keep typing, it'll just keep going because they have enough memory to last, you know, a couple hundred spots. Well, the idea is what they did is they created this concept of an exponent to short-term numbers down. It was called scientific notation, right? Where what they do is they take the decimal and they move the decimal all the way to the front to make that number shorter. So they just make this number 3.5. Right? It's 3.5, right? But 3.5 isn't the same as 3.5 million. So what they do is they use a multiplication of 10 to move the decimal. And it was a shorter way to type it, and it could fit on the screen itself. And that's why those original scientific calculators that came out from Casio, they introduced this idea of scientific notation, a really clever way of multiplying by 10 that will move the decimal, but it will display the answer like this, so it could fit on an 8-digit screen. So this number, since I moved the decimal 6 spots, this is how the calculator would display that answer, right? That number. It could fit on an 8-digit screen. And then this one back here, this is 3.2 times 10 to the third, because I moved the decimal from the back to here. Well, why I want to write this down is because I can multiply these two together using scientific notation. That's why they use the laws of exponents. They're actually doing exponents here because 10 to the 6 means you're moving the 10 6 times, right? You're moving this decimal 6 times. That's the concept. Well, when you actually multiply these together, what you're actually doing is just this. You're you're multiplying these two numbers together, and then, sorry.
What are you losing your voice?
I know it's waiters needing coffee, I don't have any.
Jaden talking.
All right,
Jaden, coffee?
Oh, no, just a
So-
energy drink.
hey, so here's the idea. When you multiply the two numbers together, you're multiplying the two digits, the powers of 10 go in the back. This is something we literally just did. If they have the same bases, you just add the powers. It's that first law of exponent we did earlier. When you multiplied items together and they both had x's, you just add all those x's together. I have a bunch of 10s. I have 9 10s in the back. Because you would add the 6 and 3 together. It's like a variable. Think of a 10 like an x. And then you would just multiply 32 and the 35 here and make sure the decimals are there. So these two numbers are something that a calculator can actually display. Like it can do 3.2 times 3.5, even no matter what type of calculator you have. Even if it's some little $2 generic thing from Dollar General, it can do decimals like that. It just couldn't do the bigger numbers because it couldn't fit it on the screen. But you get the concept that you can do it for anything. So, can somebody take 3.5 times 3.2? Just those two numbers.
11.2.
11.2? That's 3.5 times 3.2.
I think so.
Okay, so there you go. There's your number. It's probably 11.20, but you get the idea. That this is the answer. Now, the final scientific notation would be this, or if you want it in proper, where the decimal is behind the front number.
1.12 times 10 to the 10.
Yeah, exactly. And so the original calculator could display that answer, and it would fit on an 8-digit screen. That was the concept. Now, obviously, it's branched off into like crazier other mathematics with algebra and algebra 2 and pre-calc, obviously. But this was why we originally had scientific notation, was just make sure that I could do like powers of 10s. All right, questions at all about that concept? Now, my last thing to do, if you have a calculator out in front of you, here's what I want you to do. I don't know if it will actually display this, that's why I'm kind of interested in this. Okay, I want you to type in 1.12 on your calculator, 1.12. And then what you're looking for, now on my calculators, because most of you have one that looks like mine, you're looking for this little EE button. It's an exponent button. So what you do to get to that little blue button, you have to hit the second key, I call it the shift key. Second key, and then hit the little X to the -1 key. That'll put a little E on your screen, so it'll display it.
But on
So,
this one, it's an EE.
yeah, it's an EE. So on yours, you might just have a times 10 to the yeah, just so it's just right. And so when you type this in, you're typing in 1, you're hitting the little decimal button, you're hitting 1 and 2, you're hitting the little second key, and you're looking for the little EE button. Some of you just have an EE button, or a times 10 button. And then after that, all you're typing is the power of 10. You're not typing 10 to the 10, you're just typing the power that was on the 10, because the EE represents times 10. And when you type that in, it should, in theory, display either, number one, it will display this number back at you, or it will give you that full number that is literally 10 to 12 digits long of what it's supposed to be.
I just gave it right back.
It just gave it right back, yeah, because here's the problem. Yeah, the number is so big it can't fit across the screen. So what the calculator automatically does is it automatically sent it back to you as this form. It sent it back to this because that was the only way it could display it to you in the screen. Now, to prove the point, you could now just multiply these together because you guys have calculators that can do this. And if you actually hit enter, it should in theory spit this number back at you. Even if you went the other way. The reason why I'm trying to display this to you is so that you understand what that little EE button is and how it displays it to you on the screen.
That's not gonna happen. Just take it back.
Questions at all about the concept today? Okay, we're done for the day. Now, here's the idea. We have about 10 minutes left. If you have not already, I've already checked books. We have homework due today, that's page 15. If you have not turned it in, get it in the front or back basket. I know a lot of you have. You have 10 minutes to get it turned in right now. So.
Correct. I need to try this today because my car is pretty slow to go.